Session is being recorded. GA is done marking up to homework 1 to 6. Didn't you get the marks yet in your Blackboard? Homework 1 to 6 is already marked. Let me see. Let me see in Blackboard. Grade Center, full grade center. Homework 2, I see marks here for homework 2. So homework 1 and 2 is marked. If you didn't get your marks, then you should talk to me or Gia. Homework 5 marks is entered. Homework 6 is entered. 5 and 6 entered. Homework 3 entered. So 1, 2, 3, 5, 6 already entered. 4 is, I know it is in the marking is done. I don't know, for some reason it is not entered in the Blackboard, but it will be there soon. Homework 7 is not marked yet. We hope to mark it. I think the submission deadline is not yet over. It will be marked pretty soon. And the labs, let's see the labs. Lab 1 is marked. Lab 2 is not yet marked. Lab 1 and 1A are marked. 1A, I don't see lab. I'll check what happened with lab 1. Yeah, lab 1 marked, 1A marked. Lab 2 is not yet marked and 3 is not yet marked. We will do that. Yeah, that is where we stand. Midterm, I already looked at the answers. In my opinion, everyone did really well. So that will be, marks will be entered soon. Okay, so I just upload this lecture note. Take a look, and the video is being recorded. The video will be available at this link, as well as in Blackboard. I only saw that only few of you are watching the videos, so I don't know how you are studying, but you don't really need to see the videos technically, because if you read the lecture note and understand, that is how I do it. Everything is there on my lecture note. So if you read the lecture note and understand, there's no need for the videos. I mean, the videos are not produced well. I would agree with that, but it is something. Okay, so let me talk a little bit about what is optimization. So that's a connection between optimization and root finding. Colors. Root finding. What is root finding? So let's see the connection. Root finding, not root finding. So root finding is when you have a function fx, something like that, and then we want to, is a function of x. We wanted to know where the root was. So this is xr. That is when the function becomes 0. That is, the question is, at what value of x the function fx is 0. There is certainly possibility of multiple roots. For example, you can have a situation like this. So those are multiple roots. We can call it xr1, xr2, xr3, xr4. So multiple root scenario not considered in our class. That's a little bit advanced concept. We did not have. We always assume the root is 1, and then we in 3 different methods, and we always assume that we know where the roots are. I mean, the close points. We need to, most of the approaches that we worked on assume initial knowledge that is close enough to the roots. So that is root finding. Now, what is optimization? Optimization. So if we have a function something like this, optimization is finding the value of x where the function is maximized. X fx, obviously you can see here that is where the function is maximized. So we call it x hat optimal value where the function is maximized, or it could be where the function is minimized. Sometimes we look for minima. So that is x hat of x fx. Now, if we just take this example, in my previous example, this is where the function is. Those are, so that is a multiple maximas and minimas. We don't consider those cases as well. So the takeaway is we always assume, when I say assume, all the example that we will consider, we already know that they have only one maximum. We always consider cases where there's only one. There is only one optimum point. Optimal point, which is either maxima or minimum. Okay, having said that, so that is what optimization is. There's a close connection between optimization and root finding. And also, there's another connection there. Connection between root finding and optimization. So if you consider a function, let's say this is the function we want to find the maximum of. That's the function fx, x versus fx. Now, if you think about f prime x, first derivative of x against x. So let's try to sketch it. So I will make this function, I will extend this. So initially we have a around, so I'm going to move x from here all the way to see that point and what kind of values I have. So if you take that extreme left point, you have a positive gradient, so somewhere here. Let's say somewhere here, and then if you look, the gradient reduces, the derivative reduces with x, so it somehow reduces And then what is the derivative at this point? At that point, the gradient will be like this. The derivative is 0. So the function, in this point, the function will be 0. So we get the idea with something like this. So based on that analogy, I can say finding, or should I say optimizing? I already said what is optimization is. Finding x where fx is either maximum or minimum. Optimizing fx is the same as finding root of f prime x. So this is f prime x, and that is fx. So instead of finding the optimal value of fx, we can search for the root of f prime x. That is exactly one of the approaches that we will implement the Newton-Raphson method. Similar to how we had a Newton-Raphson method for root finding, there is a Newton-Raphson method optimization. So that will use this exact principle. So let's go to the lecture notes now. So that is the lecture note. Please download it from the Blackboard. We are going to study 3 different approaches: golden section search, quadratic interpolation, and Newton-Raphson method. Now, these two are golden section method. Golden section method and quadratic interpolation. This can be considered very similar to the bracketing method. So this falls under the bracketing method category, whereas the Newton method falls under open method of root finding. Now, the quadratic interpolation method, it might fall under another category called polynomial method as well. So if you want to call that a polynomial method, that's okay as well, because here we will be using approximate function as a polynomial. Okay, so those are the things that we are going to review, study in this lecture. So what is golden section method? Very similar to bisection method, golden search method. If I just zoom in here. So bisection method, we had an XL and then we had an XU, and then we will just go to the XR will be XL plus XU divided by 2, and we will just keep on moving. Obviously here we are not looking for a root, we are looking for the maximum. So what this golden section method states is that we will compute from XL and XU. We will move the XL to the right, and we will find X1, and then we will find an X2. So where X1 is XL plus D, X2 is XU minus D. So they are now crossing. X1 move fast, X2, and then this ratio is called the golden ratio. So this D, if you look at the D, well, this ratio is called the golden ratio. That is square root of 5 minus 1 over 2. I think it roughly comes square root of 5 minus 1 over 2. I minus 1. .618. That is a golden ratio. So it is greater than 0.5. That ensures that you will always pass the midpoint. So that is exactly what's happening. We will pass the midpoint and find the new points. So from Excel, we found x1. X1 is XL plus D, and then x2 is XU upper point minus D. Now we have to iterate this. So now here's the possibility. If fx1 greater than fx2, so let's say fx1, this is fx1. Oops. 1 second, please. So if fx1 is greater than fx2, so that is fx1, fx2. So if fx1 greater than fx2, we know that, so that is the maximum is between xl and x1. Is that right? Sorry, the maximum is the maximum is between x2 and x0. We know that the maximum is somewhere here. If that is the case, maximum is somewhere here. Otherwise, the maximum will be somewhere here. So that will be our new range, and then we restart the search. So that's the graphical explanation of how it works. So if fx1 greater than fx2, the maximum is between x2 and xu, and then x. The x opt is set as new x2, and then we start the iteration. Is that right? And then the whole logic is reversed. It's reversed if the range, if the condition is otherwise. It will change the otherwise. So let me think 1 second. So fx1 greater than fx2. Yes, yes. So it is between x2 and xu, and then we set the maximum as, at this point, we set the optimum point as x2, and then we start the iteration. If it is other way around, we set the optimum as x1 and start the iteration. So that's the procedure to golden search. First you understand how it works, and then we will just program it. So I just also give an algorithm for this, based on what we just, you will probably program this in the lab. So let's see what is needed. So we need a function that the function and definition needs to be on. So you need to define the function. before writing the codes. And then the golden search, it needs two input. One is Excel and then XU, and as usual, we will need an epsilon s to stop the iteration. If the relative error is less than epsilon s, we will stop the iteration. Also, always all the examples that there's all the methods, all the approaches can go wrong. That is one of the question. That's one of the aspects of the midterm question, where you will see that for some initialization it won't just work. It will just diverge. You cannot find root. So that is always a possibility. So that's always, so this is like a safeguard always, program, program, if the optimal solution can be found, we will find it analytically. Why would we write a program which will always be approximate? So that's a safeguard. If the algorithm did not converge for 50 iteration, there's no point in continuing. So, and we will find, we are looking for x hat, the optimal value. So we will set x hat based on some criteria. We need an initial estimate. So that is the initial estimate. And then we will set an iteration number because we want to count the iteration number. And then we will use the golden section method to find x1 and x2. And if x1 greater than fx2, we will set the new XL where xu remains unchanged and the new optimum value is x2. If not, I'm assuming in this case fx1 less than fx2 will be the case, else it is assumed implied. I didn't write it explicitly, but if you want, you can write that explicitly in your program. And then xu become x1 and x hat new become x1. And this is not needed. It's coming from somewhere else. And then we will compute the epsilon a. I want you to note that only for golden section method, there is a formula for computing epsilon a. Usually we compute epsilon a as x old minus x new over x new times 100. That is how we compute epsilon a. But for golden section, they have mathematically derived that formula, so it's better to use that. And that would be slightly better than epsilon a or the same as epsilon a. Sometimes it will be the same as epsilon a. So if, for example, if you implement this with epsilon a, you would probably run a little bit more iteration, but it will converge for sure. It will converge, and the other thing is probably it will converge with the same number of iterations. That is what I believe, but I never checked that. You can check that. And now you have a condition called if either epsilon a less than epsilon else or iteration number exceeds maximum iteration, you change this flag to false. That will stop the while loop. So that's an algorithm to implement it. And also for this example, there's an example fx is equal to sine x minus x squared. So we need to find the minimum. So we need to find the minimum of this. There's one more thing I need to say, that based on whether we are looking for maximum or minimum, we need to change the algorithm as well. So for example, we need to modify the whole algorithm if you're looking for maximum versus if you're looking for minimum. So it was given to start with xl is equal to 0 and xu is equal to 1. So we need two initial points, xl and xu. And then we start iteration. So we will use the formula. The x1 is xl plus d. x1 is xl 0 plus d, comes down to 618. x2 is xu minus d. 1 minus d is golden ratio times xu minus xl. So x2 comes down to this. And then we find fx2 and fx1. Fx1 and fx2 is found here, and then you check. And then if fx1 greater than fx2, you take one decision. So the whole iteration is given in this table. So initial values xl, xl, xu, those are the initial values. The computed values of x2 and x1 are here. And then we computed fx2 and fx1. We see that fx2 greater than fx1. So we will take the first rule. Fx2 is greater than fx1. XL new becomes x2. Is that right? Fx2 greater than fx2 greater than, that's the second case, sorry. XL new becomes XL new becomes XL. Yes, XLU becomes XL. XL just carries forward. XU new becomes X1. So you see X1 becomes XU new. This one just carries to the next one. So that is XL new is XL, XU new is X1. Now you compute X2 and X1 again using the same formula, and then you find fx2 and fx1. Now this time you check, you find that fx2 is less than fx1. So you will just select the next one based on that. So then XL new becomes X2. So you'll see that X2 becomes XL new. Then XU carries down. And then you compute X1 and X2 using the formula. This time again, same, fx1 greater than fx2. So this just carries down, and this one goes here, and compute the new x2 and xu, and then this time it is the other way around. So now you know the drill. This one goes here, and then this one carries down, and it goes. So that's the iteration. So that is the algorithm here to find. So I just so this algorithm, maybe I will add this comment. So this algorithm is to find a minimum. So above algorithm has gone. So the above algorithm finds minima, and it must be appropriately modified to find a maximum. So that is Golden search method. It is, the drill is the same. There is nothing much new in the optimization methods. It's very similar to root finding. Algorithms are the same, and then the approaches are the same: bracketing versus polynomial versus open method. So yeah, you may have to. There will be one or two questions for homework. I would suggest writing a program to find the answers, but you can also do it by following the same table approach that I'm doing there. Okay, so the second approach for root finding is quadratic interpolation. This is very similar to root finding using quadratic interpolation. We had a quadratic interpolation approach for root finding as well. That approach, we started with 3 points. in this, okay, here we will start with 3 initial points, x0, x1, and x2. So we need 3 initial guesses, whereas the golden section method required 2. Here we will need 2 initial guesses. And we will use these 3 points to fit a parabola through these 3 lines. So that is the parabola shown here. The true maximum is shown here in the dashed line is the true function. We fit a parabola through those dashed lines. Sorry, this is the parabola that we fit. We fit a parabola. So once you fit a parabola, you can use the maximum. You can find if the parabola is fx is ax squared plus bx plus c. So where it is, its maximum is where, or minimum, if you just take a derivative, prime x is 2ax plus b. If you set it to 0, x is minus b over 2a. So that is where the maximum is. So x3, if you know all of this, it is minus b over 2a. But how to fit the parabola, all of that is taken care of in this equation. So that is the advantage of this approach. This equation does many things. It fits a parabola through those 3 initial points, x0, x1, x2, and it finds where that maximum is, and it gives you as a formula. This formula, x3, given by equation 2, achieves all of that. It fits parabola through 3 points. Let me show those 3 points. Those 3 points are x0, x0, x1, and x2. If you look at this here you only have x0, x1, and x2. So it fits a parabola and finds where the maximum is, everything in the formula. So the only downside is we need to know that formula. So if we don't know that formula, we cannot proceed. So that's now how to move to the next step. So I gave a rough sketch of the algorithm. I want you to fill that out. So here is how it is going to work. So this is an algorithm for quadratic interpolation to find the maximum of a function. So we know that it needs input x0, x1, and x2, and it needs epsilon s to stop the iteration. It also needs maximum iteration to stop the iteration. So we need a initial guess x hat old. So if you have 3 points, if you have 3 initial points, you can come up with a way to find, for example, if you have these 3 points, and obviously in this example we are looking for a maximum, which one will be x hat old? X1, this will be x hat old. Why? That has the maximum value compared to all of these. If you just look at this, that one has the maximum value. So you can write a program for that. I just gave the hint saying it's argmax. So max it is find fx such that x fx is maximized for out of these 3 points. So you compute fx0, compute fx1, and compute fx2, find which one is the highest, and then use that as the initial point. And then one simple formula, easy formula. We need to know this formula, but this does what this does. It fits a parabola through that and find the next point where it is maximized. So that is there, and then you have to come up with a rule. Okay, what is a new x0, x1, x2? That we need to out of the previous x0, x1, x2, we had to get to the 1 and bring in the new x3 because that is the latest. So I did not write the rules for that. I left that for you to fill. So once you have the new x0, x1, and x2, and the new optimal value x hat new, I call it x hat new. So you have an x hat old, which came from the previous time. and exit new, and then we can use that to compute the relative percentage relative error here. So you compute the percentage relative error. Now we are ready to check are we good in terms of accuracy, required accuracy, and we compare the iteration number, and then we do two things. We increase the number of iteration and put the old value, the new estimate in the old, and the while loop will start. So that's the code. I mean, that's a pseudocode for the polynomial method for optimization. I have one more method for optimization. Again, very simple method based on what I just talked about in this. Okay. So here, so it is, if you want to find out optimize a function, is equal to finding a root of f prime x. So equal to finding the root of the first derivative. So with that, we know that this is the equation. If you just go back to your open methods lecture, I think lecture 5, you will find that this is the Newton-Raphson method for root. Newton-Raphson iteration for root finding. So what we want to do now is, instead of root finding, we want to find the roots of f prime x. So if root finding of fx. So to find the root of f prime x, there's only one thing. Here it is xi minus fx over x prime x. Here it's going to be xi minus f prime x over f double prime x. That's it. That's already different. A very neat formula from Newton. Okay, so we will use this. Is it the same example? Sin x. Now it's a different example. Find the minimum. Find the minimum of. So probably I should. So this algorithm. There is another remark here. So we have to. We will decide. For example, in the previous algorithm also, the algorithm is. It is hardwired to either look for a maximum or minimum. Same here. When you fill this, you will hardwire it to either find a maximum or minimum. Now for the Newton-Raphson method, it doesn't really know whether it is a maximum or minimum. So if you let me go to the algorithm, then I will elaborate that. So this is a function. So unlike the other approaches, Newton-Raphson method only requires one initial guess, and then these two regular inputs. So we will say the x hat old is x0, the initial guess, initial optimum value of the function. And then we will compute f prime x old, and then compute f second derivative of x hat old. And then x hat new, I'm just showing the formula, x hat old minus f prime x old. Okay, that's a typo there. That should be x hat old. There's no new yet. So that is a formula, and then you find the percentage relative error, and then the iteration will go on until so you will do this and go to the while loop. So this algorithm doesn't know whether it is maximization or minimization. So this algorithm, the same algorithm for both maximization and minimization. So this algorithm is the same for both algorithms, both maximization and minimization. So so the advantage is that most of the time we know whether we are looking for a maximum minimum. For example, here it is asked find the minimum. So we know that through the question that we are looking for a minimum, but we don't need to tell the algorithm here because it's the same routine. For example, if you're given another function asked to do a maximum, all the steps are the same. But for example, instead of giving this, someone might give a function. Okay, the function is given. Find the extreme point. The extreme point could either be maximum or minimum. But we also need to say whether that is a maximum or minimum. So if you don't know that, I'm sure you took this in math. So in calculus. So you take the second derivative, and then if the second derivative is less than 0, at that point, at this x hat opt, you find the optimum point, x hat opt. If the second derivative is less than 0, that point is a maximum. If the second point derivative of x hat opt is greater than 0, that's a minimum. So why is that? Because it is so this, if the function is maximum, if the function has a maximum, the first derivative, this is called a decreased function. I'm just refreshing you. This, you must have studied this in calculus. So this is a decreasing function all the way. So a function is decreasing, called a decreasing function if its derivative is less than 0. So if it has a negative derivative, it is called a decreasing function. And so f prime x is a decreasing function, which means second derivative of x. So the derivative of this is negative. Derivative of this is negative. Negative. If we had a minimum, everything will be opposite. If we have the function that has a minimum at that point, then the first derivative will be increasing. So derivative of that will be positive. Okay, so that's how we will. So that's a summary of Newton-Raphson method. An example is given, and then some steps are, some results are given. The best way for you to check is to write a code and check it, or you can just do it by hand as well using a calculator. So that's an easy lecture, because it is very similar to root finding. There are a couple of questions. I would encourage you to take a look at them. I will assign one or two of these questions for homework. I'm not going to assign one homework for each lecture anymore. I'm going to have one homework for 2 lectures. So the next lecture, which will be recorded for Thursday, and then there'll be homework covering these 2. So since there is some time, let me quickly say a few things about the next lecture. So that's, first of all, that's all for this lecture, optimization. That's a very short lecture. So that is called one-dimensional optimization. Actually, I wrote this, but I did not talk about this, one-dimensional versus multi-dimensional. So let me talk about it now. One-dimensional versus multi-dimensional optimization. So even though I'm going multi, I'm going to say 2 because I'm going to discuss an example that is 2-dimensional. But the argument is the same for multi-dimensional. So if 1-dimensional optimization, we were looking for a function fx, and then where the function has maximum, or minimum. So this is what we were looking for, x at all. But think about a function. We need some imagination here. Think about a function in 2 dimensions, x and y, and then we have a third axis. So this is a 3-dimensional scenario. This function is called fxy. Now, we have a function like that, that it's going to be a surface. And then we want to find out where that function has a maximum at that point. That is going to be x hat opt, y hat opt. So that is an example of a 2-dimensional optimization. If you go back a little bit on this, you can ask the question, shouldn't there be an analogy for this in root finding? Because in root finding, we find the root of all the example that we in the example we were just finding the root in 1 dimension. Shouldn't there be an example of a function multiple? If we have a function, actually in the I have an example here. I mean, there are examples in the book or textbook also. In my lecture 10, I gave an example at the end. And take a look. I'm going to write that down. So there is a function fxy is 2xy plus 2x minus x squared minus 2y squared. That's a function of 2 variables. So we can find a root for this function as well. Maybe, for instance, that function would be this. That could be fxy. So when we are finding a root, we are finding when that function becomes 0, at which x, y values. Most likely, it won't be a point. It could be a line. The function, if you just think about the surface, it will just maybe it will become 0 along this curve. That is root. So root is not a point. It could be a line. That is one thing. And then I hope you get the idea of how to find the optimum value is going to be adjusted for this case. For 3-dimensional case, the optimal value is a point. But if you just think about 4-dimensional, which is hard to imagine, but then if you think about 4-dimensional, the optimal point, that will be a line. And for the next dimension, the optimal point will be a surface. Let's not go there. But I'll tell you one more thing. So we did one whole lecture about multidimensional functions and finding their root. That is, if you think about it, that is the linear system of equation. So what did we have there? We had a system A, x is equal to b. Technically, you can write it as fx. So that is what we were trying to solve. I can write it as ax minus b. These are all vectors and matrices. A is a matrix, x is a vector, and b is a vector. Ax minus b is equal to 0. And then I can write as fx is equal to 0. And we are finding values of x such that fx is equal to 0. So we are basically, technically, we were finding roots. By solving the above, we were technically finding roots. Okay, so that is the multidimensional root finding, which is we had in our linear system. We had many methods, many specific methods. Since it is linear, everything that we did was optimal. Our next lecture is going to be the same. We are going to do optimization, multi-dimension, many variables, but things are linear. Since they are linear, there are very specific methods to do that. It is called linear programming. So that is the next lecture. Sorry, linear programming. So it is a special case of multidimensional optimization. Similar to how all these methods, Gaussian elimination, Gaussian elimination, LUD, all a special case of root finding. Well, I should say multidimensional root finding. So what we want to do is the general case, the one-dimensional case that we did so far is a general case. Any nonlinear function, we can find the optimal value, which we are not going to do. So when it comes to multidimensional, we are limited in this class to only linear functions. So we did do multidimensional root finding, which is basically linear system of equations. We had a different name for that. Similarly, in the next lecture, we are going to do multidimensional optimization, but we will call a different name for that because everything is special case and things are will find perfect solutions because it is linear. So that's just a brief introduction to the next lecture, which I will record separately and upload it there. So we just a reminder that you will have a quiz on Thursday at 11:30, and best of luck with your remainder of the midterms. I am here if you have any questions. Yeah, I will. How many days do you want? Do you want me to extend up to when? Lab 4. Somebody is asking it's an extension for Lab 4. If you want, you can do this. You can just because I didn't get a lot of requests from students. So if you want some extra time, just send me an email. I will give you personally some extra time to do this. But I still want to keep the deadline because honestly, there were many requests, and I want to also we want to start grading the labs. So if you need some extra time, send me an email. I will give you extra time without any penalty. All right, everyone. So I look forward to the live class on next Tuesday. In the meantime, you will see a recorded lecture on Thursday about linear programming. Have a good week. Let's stop recording.